Good morning. My name is Eric Robinson. I'm here representing the Green Launch team and the Green Launch technology. So I'm just going to give a quick introduction of our team. Our corporate technical officer, Dr. John Hunter, is here. Our financial and engineering genius, Rob Fryer, is here. And then our PR and government affairs expert, Brad, is here also. The only member missing is our CEO, who is Don Whitney. He's an ex-B-52 pilot. He runs an environmental company, and he wasn't able to join us today. So my name is Eric Robinson, and my company provides fluid delivery systems for satellites and for spacecraft. I've got parts on Mars on the Curiosity rover, and I've got parts in the asteroid belt, the Dawn mission sitting around somewhere out there, and then mostly communications satellites, ion propulsion. So that's my space background. So Henry Ford once said, if I asked people what they wanted, they would say faster horses. So we do have a need for a quantum leap here. You've got to start thinking a little bit more, outside the box, as they say. And so what we're looking for is a quantum leap, a new way to get to low Earth orbit. So once you're to orbit, you're halfway to anywhere. And we can use this methodology to get food, fuel, water, construction materials into orbit and small satellites. Green Launch will play a pivotal role in delivering acceleration-tolerant payloads cheaply into low Earth orbit, and you can use that to research the atmosphere. You can use it to refuel on your mission to Mars or conduct small satellite launch. What is the problem, really? Well, the problem is we live in this huge gravity well here. I mean, Earth is the biggest rock in the solar system. Anything bigger than us is a gas giant. So that's the problem. We've got this huge gravity well. We're trying to get up into orbit. And the problem with our existing system is that rockets are expensive. They create pollution. You wait a long time to get on one. And so there's issues there that our customers are hoping that we can find a solution to. Right now, NASA launches for about 5,000 a payload pound. Elon's getting down to maybe 200 a pound. We're talking about $200 to $100 a pound eventually for our final offer. And we're going to pave the way for a lot of orbital businesses that are just simply can't get off the ground today. What is the history of impulse launch? Well, right now the world record for ballistic launch is with gunpowder is 110 miles. So that's, people have gone to space suborbitally with ballistic launch, and we're going to use something called a hydrogen-powered high-acceleration impulse launch system. And this system is reliable, it's cost-effective, and it doesn't produce any pollution except for a little bit of water vapor. This is a system we have at Yuma Proving Ground. This was last month. So just try to get an idea of what the velocities we're talking about. Superman is faster than a speeding bullet. So a speeding bullet's about 1 kilometer a second. I mean, so we're going to be operating at between 5 and 6 kilometers a second, our cannon, or our launch system. And what do you need to get into Earth orbit? You need about 7.4 kilometers a second. So with our system, we got 5. We need to add an additional about 3 or so. So we'd have a small rocket. So initially, our payload projectile would be up into orbit and into space, and then the rocket would circularize that orbit. But for things like Mars, the escape velocity is 5, which was basically our speed. So you can get to escape velocity from Mars, and you can also get off the moon 2.4 kilometers a second. So we can obviously do that also. And so this is kind of an artistic design of a very primitive version of what we're going to actually be building in the near future. So whether we're doing hypersonic testing, we're doing sounding rockets, so we wouldn't need a sounding rocket. We'd just use our orbital system to take us up into the same altitudes as sounding rockets, or CubeSat launch. All the trend lines are fantastic at this point. Everybody's launching into space. This is the Space Force. They're obviously going to need some way to get people and material into space inexpensively. And this is the satellite launch market. So our first product offering will be 5 kilograms into orbit. That's a P-pod, 3 CubeSats together, and that's our first commercial, well, it's actually our third commercial goal. Our first commercial goal is hypersonic testing on the ground, which we're ready to go for now, and then suborbital, like sounding rocket replacement, and then third would be the orbital 5K. So many people are trying to capture this microsatellite market, but the key is simplicity is the key to reliability. Reliability is the key to price. And once we've got our facility constructed, we'll have a competitive advantage over anyone. We can put things into orbit very, very inexpensively. So this kind of gives the current market pricing, and we can do that. We can do it for about half and still remain extremely profitable. So what do we need to do to get payloads ruggedized in order to be able to withstand the G-force of this type of launch methodology? And basically, it's simple epoxy. For most electronics, you can use simple epoxy to ruggedize them to withstand the G-forces that we're talking about. I mean, even now, if you drop your cell phone on a concrete surface, it can see about 6,000 G in deceleration. So electronics are already G-hardened to a large degree. Yeah. Oh, wow. That's Dr. John Meyer. Okay, I'm sorry, go ahead.
Thank you for the presentation. You're talking about the G-forces, and we're thinking about that sharp acceleration to get into orbit. What kind of thermal challenges will you have for making sure that your payload is secure given the speed of orbit?
Yeah, so our orbital projectile is an aeroshell, and we have a sabot, which gets us out of the barrel. The aeroshell gets us through the atmosphere. This has a carbon-carbon tip on it. It's ablative. It takes the heat away. It erodes down 6 inches. So this is technology that already exists. So that's not a huge problem for us, and that problem's already been solved.
So this looks to me like a rejuvenation of Project HARP back in the 60s that the military was, and I think you probably know, there's one of them is sitting on the ground in Yuma, the other is on a beach in Barbados. Can you tell me a little bit more about why you felt that the military abandoned the project? Was it because of the advancement of the technology wasn't there yet?
So they were using gunpowder, and like I said, they own the world record today. It's 110 miles. Gerald Bull was a ballistics genius. We know people who were part of his team. They were grad students at the time, and the people we're in touch with now. So he's got a great legacy. He obviously had financial issues. We stopped funding him at one point, and then he went to work with South Africa. He got busted. He went to prison. He came out super angry. He went to work for Saddam. He was assassinated by Mossad. So, I mean, we're not going that route. We're not going to go that. We're going to try to avoid the mistakes made by Gerald Bull. And, yeah, we're going to go commercial, and we're not going to go into military, and we're not going to work with anybody in Iraq at the moment.
Well, following up on that, though, I totally understand what you're saying here. So I've seen another project like this. You're probably aware of New Ascent, which I've been aware of some guys out of Orbital ATK that came. I spoke to them about this very similar a couple of years ago.
Right.
Tell me if I'm wrong, but I'm assuming you're not going to get to orbit by just firing your sabot. You're going to have at least some propulsion system to get you into a circularized orbit. You're going to get to altitude, but you're still going to need a propulsion system to get there.
That would be the replacement for the third stage. So the third stage does bring us an additional 3K. We need to get a little more velocity. We're shooting at 5 or 6. We need to get to 7.4 and all to circularize. So we do have a rocket stage for the last part of it here. For the Moon and Mars, you don't need that to get to escape velocity, but for the Earth, you definitely do.
I was kind of curious how this scales the market for 5 kilograms or less. I mean, there's definitely a market there, but it's pretty limiting. It seemed from your materials like you were thinking of scaling up, and I was curious how high you think you can go, how much that would cost. Does it scale linearly in terms of cost, or?
Yeah, it does. It scales photographically. So the bigger the diameter of your barrel, the longer your tube has to be. So we can go up to a metric ton. It ends up being, like a kilometer long. But this is just basically tubes. There's nothing really complicated here. Totally simple. The fastest gas in the universe, hydrogen, and that's, if you put all the molecules in a row and let them race, hydrogen wins.
Can you give any sense of what that cost would be if this actually took off and the 5 kilogram tests were successful and you had a little bit of a market there? What would be your next step and how much would you need?
So I think after 5, we'd go to maybe 50, go to 100, and then eventually up to, 1,000. That's our goal.
I was thinking that this is very similar excuse me, to linear accelerators. Is there a lot of the technology that's coming out of the linear accelerator Department of Defense programs that could be useful here, or might a linear accelerator be better suited to this kind of goal than hydrogen?
So so the magnetic guns, electric guns, coil guns, we're all talking like 4.5 kilometers a second. The world record for hydrogen guns, 11.2, 3 times. And those guys are complicated. A lot of things go wrong. You got, the extra projectile fuses to the barrel. I mean, you got huge energy requirements, so many different problems. This is super simple, super cheap. It's just basic plumbing and one-dimensional gas dynamics.
How portable is this? Is this something you can pretty much just do it anywhere, or do you need to have a pretty heavy-duty in-built facilities? It seems like they're fairly big, but not enormous. It was hard to tell from the pictures.
So this is kind of a picture of what this thing looks like. At this point, it's about 55 feet long, and here we are accelerating almost 2 kilometers a second, and that's sparklets. Oh, missed the sparklets bottle. Anyway, so yeah, this thing can be scaled, and it can be. This one's on a carriage right now, but eventually the systems will be probably stationary, and we'd like to be able to change orbit and different inclinations. So this possibility we'll have it so we can change the angle this direction, and then maybe also changing radially. So yeah, a lot of flexibility there.
So in order to have the high G acceleration for your small CubeSats, they're going to have to be solid state or something, obviously, I'm thinking.
Yeah, so this, it's a matter not so much of G, but of stress. And so you want to have short, low components that aren't implanted, but probably onlaid, on components, on insertion. So it's meant to, you can test things, we can try them out. We'll give people a test bed to try things out in our test facility to make sure their payloads can withstand the G-force. And I think it'll be a 10% engineering cost NRE up front, and then they can use this methodology from then on. Hey, you're welcome.